Our first speakers this afternoon are Frank Gordon and Harper Whitehouse of Innoval. They'll be talking about the LEC, and the title of their paper is Scaling Up the Lattice Energy Converter, an Electrophysical Direct Conversion Device, LEC EDEC. So I'm going to hand it over to Frank and Harper.
Thank you. I'm going to use a mic and walk around, and then Harper's going to stay seated. So that's how we're going to do the presentation. I'm going to start with a little bit of an update and reminder. I suspect most people here know this, but in case you don't, the LEC will self-initiate and self-sustain the production of a voltage and current. Naturally, radioactive materials are not required. The current and voltage produced is non-ohmic. In other words, they don't go to zero together. Current does not saturate under electromotive force is increased. That's something that's different from what J.J. Thomson found in his experiments. These results are repeatable, and as we've learned, multiple people have replicated these results for gaseous LECs. So I would hate to stand up here and say all of those things if it weren't for the replications by various people in this room. So what is a LEC? We call it an electrophysical direct energy conversion device involving contact electrification, hydrogen included, hydrogen host material, different Fermi levels with continuously readjusting equilibration. And it can be described and analyzed by considering drift and diffusion and the stochastic electrode wall impacts. So one of the things we haven't done in the past, because we didn't know, is talk about how we think this works. That's going to be the focus of this presentation. Here are a couple of pictures of examples of the LECs. The one on the left is the cylinder, the one that we started out with several years ago, where we show it with an external power supply, which, so we can actually apply an external voltage or an electric field inside the LEC. The one on the right is the plain parallel LEC, and actually that's the one that we're working with more now. It's a lot easier to construct and control the separation distance, which is very important. And what happens is when the electrodes are connected together, the Fermi levels in the two electrodes will equilibrate. And if there is no electrolyte in between, nothing happens. It stops. If there is an electrolyte in between the electrodes, they will try and revert to their natural Fermi levels, which means they would be transferring electrons, and that then will cause the external circuit to re-equilibrate. And so as this continuous process goes on, this is how we believe the current is being produced. There are three operating regimes for the LEC. The one on the left is the diffusion dominates. This is where the electric field is very low, and at this point it's thermal energy, then the molecules and ions bouncing around, and that's very low. At the far right, the voltage and electric field dominate, and you can see at the far right how it's again pretty low. Power in the middle is where the voltage is approximately equal to the diffusion. This is not unusual for power supplies, but this explains where the power is best. And I've got this on the bottom just to show we've done a lot of experiments in air, and air is only a half a part per million of hydrogen. So unfortunately, if you do it in air, the hydrogen tends to come out of the palladium hydrogen host material, and we lose the benefit. And so cells that we have had operating in a hydrogen environment have operated for years. In fact, the ones that we took to Texas Tech to have the gas analyzed had been operating for years. Ones that, one of the reasons I was going to bring some cells here, but transporting them in a hydrogen environment was going to be an issue. So I've got some pictures of that. Okay, an obvious question. I mean, this thing looks pretty damn simple. And why wasn't it discovered a long time ago? And the simple answer is that not all the pieces were known a long time ago. It starts actually 2,600 years ago when a Greek scientist and philosopher named Thales discovered the triboelectric effect, and he realized he could rub a rod or something and pick up pieces of paper and it was magic. They didn't know what it was. When Volta was doing his contact potential work, he accidentally discovered electrochemical reactions, which ended up being a battery, so that wasn't all bad, but it diverted away from the work he was doing. But the key is that when 1989, when Pons and Flashman came out with what we all know now, and the work that Stan Spock did in the way to load hydrogen into the palladium, that is a key. When we conduct experiments without those materials, nothing happens, even though the physics itself indicates that you would be able to detect something, but it's below the sensitivity of our instrumentation. Okay, so this is another question, is how is this thing producing 10 to the 14th or 10 to the 15th electrons? You know, 100 microamps doesn't sound like a lot. 100 microamps per square centimeter doesn't sound like a lot, but an amp is 6.24 times 10 to the 18th. That means 100 microamps is 6.24 times 10 to the 14th electrons per second per square centimeter. Try and do that with a nuclear, and how many thousand curies are you going to need to do that? And we don't see any radiation. Bark didn't find any radiation. In fact, Harper and I think maybe they didn't find anything because there isn't any. So how do you do that? Our experiments, some people have reported, in fact, when I was at SPAWAR, we reported some soft X-rays. We published articles where we detected with CR39 some particles, alpha particles, and so on, but nothing near the number that would be needed to come anywhere close to the amount of current that we're seeing. So to produce big numbers out, and certainly 10 to the 14th, 10 to the 15th is a big number, we want big numbers in. And so our electrophysical model involves the work function of the electrodes, contact electrification and tribofusion, Fermi levels and Fermi level equilibration, Lock-Spitz number, there's a big number for you, 2.68 times 10 to the 19th molecules per cubic centimeter in gas at STP. The Maxwell-Boltzmann equations, the kinetic theory of gases says that we will get at one room temperature, and we will get 1.14 times 10 to the 22 wall impacts per square centimeter per second. And not shown on here, but the speed of those molecules, the average speed at room temperature is 1,700 meters per second. So there's a lot of activity going on in there. And with quantum mechanics, and we believe this is how it's happening, and what this does, this model that we think we understand now, opens up a lot of things in the design and materials that we use and the flexibility. But as I say here, the PDH and active material is required, and these include big numbers in. In fact, when you start looking at this, you can say, why are you only producing 10 to the 15th when I've got 10 to the 22nd here and 1,700 meter per second and 10 to the 22nd? And maybe there is more that we can harvest now that we understand it. Okay, so what is the model? And basically, you've got two electrodes with different work functions, and if I connect them together, through an external load, their work functions, their Fermi levels will equilibrate, and then nothing will happen, and it just sit there. But if an electrolyte is in fluidic contact with the electrodes, they will attempt to revert to their native Fermi level state. And so if the high work function electrode is able to, he's got too many electrons, if he's able to get rid of an electron, then that causes the Fermi level to change, and the low work function electrode will say, here, have another electrode through the external circuit. That's our current. And the same thing happens at the low work function electrode. So this is how the current is being produced. That's how we believe. And as these electrons are continuously transferring, we have the current continuously being produced. And so that is the model. And electrochemical reactions are not required. And according to this model, the hydrogen host material and low energy nuclear reactions or whatever it is, they aren't required either. But as we've said, it doesn't work, or at least it don't detect anything without it. And as I say, it's not required, but extremely helpful. This is a pictorial of what I just described. So we have here the external circuit. We took the two electrodes together through the external circuit. We hook up a DVM. The one thing we absolutely know is how much currents that we're collecting, because that's a simple thing to do. You record the voltage across this resistor, the variable resistor. So that's the one thing that we really know. Inside, then, we need to find a way to transfer electrons from here down to here. So, that's the opposite of what you would expect. Typically, electrons will be attracted to the high work function and be not at the low work function, would avoid them. So something is in here, and that's what the electrolyte does. But there are ways, we think there are ways to do that, and certainly the energy of the molecules as they slam in to the various electrodes, and the triboelectric effect may be the way that happens. So I think I've said this about 3 times, but so this caused us to say, okay, well, what properties do we need in that electrolyte? And it really comes down to a couple of things. It's got to transfer electrons from the high work function material to mobile ions in the electrolyte, and then they have to transfer that electron to the low work function material. And this electrolyte can be a gas, a liquid, a solid state, even semiconductor, and we've tested several of these, the gas, liquid, gel. The solid we tested by accident when we were using high temperature epoxy as an insulating material between the 2 electrodes. And when we raised the temperature up, the thing worked great. We later realized that was because the epoxy, at above about 110 degrees C, the epoxy began to act like an electrolyte. And our curves looked a lot like what John Paul showed yesterday, only our bend in the curve started about 110 degrees C. So there are lots of different electrolytes, and in fact, semiconductor material may be a real winner when we get down to this, and I think I'll show that later. So that's an interesting model, but is there any supporting analysis? And having raised the bar that high, I'm going to say, Harper, why don't you take that one? So I'm going to turn it over to Harper to respond.
All right. So now the first curves that you saw were done at 130 degrees centigrade. Just to show you that this really isn't a critical feature, these are the curves of the cells that we took to Texas Tech in order to have the gas analyzed. These are operating at room temperature, approximately 26, 27 degrees C. And you see that the curves are exactly the same thing. We see that there are 3 regimes: a diffusion regime, a power production regime, and a drift dominant regime. Contact electrification, active hydrogen included host material, and the Fermi levels are the things that make the LEC operate. The first produces the contact potential difference. That was discovered by Volta years 1800. The second significantly modifies the electrolyte ion dynamics, And finally, the Fermi levels determine the unnatural distribution of electrons in the electrodes. The challenge, though, is to find exactly what the hydrogen-occluded, hydrogen host material is doing, and we have no idea. So we will approach it from just a phenomenological point of view. Two approaches can be taken. We can determine things on a deterministic basis. These are the mean properties of a gas, and these are diffusion and drift in an electric field. Or we can go with a stochastic model and try to take into account the random motion of the molecules and ions. Starting with the simplest one, what you do is have never been able to solve the differential equations analytically. They were first written in terms of a complete set of equations by Edward Ricci in 1903, 120 some odd years ago, and we still do not have an analytic solution. So what one does is one simply ignores the things that are causing you problems, and take a first cut, and then try to correct the solution subsequently. All right, let's now take a look at what we can do here. All right, here are the equations.
One more.
Yeah, I want the equations. I have equations coming up next, but
Okay, your slide's out of order.
my slides are out of order. All right, well, we've said that. These are the,
Okay.
okay. All right, what we're going to do is, unfortunately, we have notational changes that we have to deal with. We will call the density of the ions either the density of positive or negative ions, but in the literature, for historical reasons, they're designated N1 for positive ions, N2 for negative ions. Okay, and basically we have two, as I said, time scales of motion that we're going to consider. All right, next slide. All right, that's the same slide we just had. We're going to, all right. Now, these are Ricci's equations. However, they have been rewritten in modern notation that was introduced by Darrow, a physicist at Bell Laboratories, in about 1932. The first three equations sort of tell the story. The first one, Poisson's equation, relates the density of positive and negative ions to the derivative of the electric field. But the electric field is always of the same sign, and therefore when the voltage goes to zero, the electric field goes to zero, which says that the gas contains approximately an equal number of positive and negative ions. Then we have the two charge conservation equations. The important terms are, we see there, the electric field term on the far right, the diffusion term with the coefficients D1 or D2, and we see the problem child, which is the alpha N1, N2, which is the ion-ion recombination that is taking place in the gas, and this keeps us from recovering all of the charge. For the people who make ionization chambers, they simply hit the device with a high voltage, overpower the field, and sweep the ions out. Now, Darrow made an interesting observation. If you extract equation 64, one from the other, and integrate once with regard to the spatial variable, we now get an equation that involves the current density I on the left, the electric field drift on the left there, and the diffusion term on the right. And we see that that diffusion term depends upon both the coefficient of diffusion, the diffusivity, and the gradient of the ion density within the gas. And unfortunately, some people have made numerical solutions to the differential equations. They did this about 1960, and they set D2 equal to D1. Well, that doesn't quite cut it in terms of what's going on in the cell. All right. As I said, since the electric field is constant, always the same sign, when we see that the voltage goes to 0, we can therefore conclude that the number of ions, N plus and N minus, are approximately equal. Now, this one, oh, there we are. All right, here's one that I get criticized for, but I like it. Here's basically a plain parallel leg. You have a low work function material on the bottom, high work function material on top. Doesn't run unless we put in the magic hydrogen host material occluded with hydrogen, which in this case has been shown up in the high work function electrode. And the electrons go up through the load impedance, and the circuit is completed by electrons being transferred back through the gas or through the liquid. All right, this then is sort of the explanation that makes it all work. You take the two materials, with high work function, low work function, and as Volta discovered 200 years ago, connect them together, and electrons transfer from the low work function material to the high work function material, and then a potential is set up, and the potential is the difference in the work functions, which are energies, and of course to get a voltage out of it we have to divide by the charge on the electron. So now we know what the voltage is in the cell as a function of the materials, and so we have now a well-defined metallurgical problem to choose the materials, one which is low, one which is high, and which don't react chemically. And the question then is, we've got perpetual motion. That doesn't go over very well. And so the question then arises, and this was answered by Irving Langmuir in 1916, who worked at General Electric, where does the energy come from that supports this continuous flow of current? Well, the energy comes from the energy required to ionize the gas. Now, for this audience, what's ionizing the gas? It's the hydrogen-loaded, hydrogen-host material. The palladium black or iron black works just as well as the Stefano showed. So we now know the source of the energy. Well, that's a good possibility that that's LENR. Now, problem is that we want to transfer electrons from the high work function material, which has a positive voltage, because the electrons are flowing from the low work function up to it. Therefore, by definition, conventional current flows from the high work function to the low work function, and it's positive. So this means that we have to do uphill or non-frequent diffusion. All right, well, turns out that K.K. Darrow pointed this out, again, many years ago, that when the potential difference between the electrodes is small and therefore too low a field strength, some of the ions will be lost by recombination. Those are the ones we have to recover, and by diffusing to the wrong electrodes. But the ones that are diffusing to the wrong electrodes are the ones that make the LEC operate. All right, so now we need to estimate the recombination loss. That we can do following J.J. Thomson. You simply make an assumption here. We're going to, like I said, neglect the term that causes us trouble. We'll just neglect diffusion, solve the equation, and we find that the density of ions in the gas is the square root of the rate at which they are being ionized divided by the recombination coefficient, which is a number almost the same for most of the common gases, which is something of the order of 10 to the minus 6 cubic centimeters per second. Well, what would happen if you included diffusion? Maybe that will cure the problem. People at CERN, in a lovely paper that was published in 2015, went ahead and addressed the problem and solved the differential equation, which is a little tricky to solve. based on the work of Israel, which was done a few years earlier. And when you cut to the bottom line, we see that you get exactly the same answer. If you include diffusion, you still get that the number of ions in the gas is the rate of ionization divided by the recombination. So we know the gas contains a lot of ions that we are not collecting in the resistance and turning into electrical power. All right. So what can we do? One of the ways we can do this is we can observe experimentally that the LEC performs best, maximum power output, when diffusion matches drift. We've got two competing terms. One was helping us, one's hurting us, sort of like in designing a transformer with copper loss and iron loss. You just set them equal. So let's go ahead and try evaluating these terms and see what we get. And if we do that, we see that the drift term, when we get through making the approximation, which again is a somewhat crude approximation, that the voltage, that the electric field is the voltage divided by the separation of plane parallel electrodes, we find that the time constant for drift is d squared over mu b leg. Now, it's a little trickier solving for the diffusion time constant, so we'll invoke McDaniels, who does that for us, and he shows us that it's d squared divided by pi squared times the diffusivity. But we know from the Einstein relationship that the diffusivity can be written as the mobility times Boltzmann's constant times the temperature. And so we see that if we can get the ions out of the gap before they have a chance to recombine, we have a chance of getting the improved performance. And we see that that depends upon d squared. Very small separations. This is why we've gone to parallel geometry, because it's a lot harder for us to try to make small separations in the cylindrical geometry. And we typically use Teflon tape, just 1 or 2 layers of Teflon tape, just enough to keep the electrodes from being shorted. Well, since we are going to make the approximation that the two time constants are equal, we see that the only thing that's left over is the voltage and the temperature. And we evaluate that at 300 degrees K, and we get a not bad approximation. Says a LEC should produce about 255 millivolts. It actually produces closer to 400, 450, and the explanation is shown in the next slide, because, as I said, I used an approximation. Me in 1904 actually solved for the electric field distribution between parallel electrodes, and you can see that the approximation of D divided by the voltage is really a not too good approximation. We believe that counts for the slight difference, but I would say within a factor of 2 is good enough at the present time. So let's now move on and see if we can do something with the stochastic. This is, again, the same problem we had before, except now what we're going to do is we want to look at the number of wall impacts. The wall impacts are what provides the pressure. When you've got gas confined in a bottle, it's the momentum that's being transferred to the wall that defines the pressure that the gas is operating at. So what we do then is we want to examine the question. We'll simply use very basic kinetic theory of gases. We'll simply assume that the collisions are inelastic and that the molecules have a Maxwell-Boltzmann energy distribution. Okay, let's look at what that distribution is in the next slide for those who may have forgotten what it is. This is the distribution. We see the exponential on the right, which is the active part. That's the energy divided by the Boltzmann's constant times temperature at 300 degrees C. That's approximately 25 millielectron volts on the right. All the rest of the terms there are the ones that are normalizing the equation in order that this have a unit area. I don't know, I can't have trouble seeing this, so let's plot it. And here we see the Boltzmann distribution plotted for 3 different temperatures, and we're interested in the tail. And in particular, we're interested in the activation energy. That is the energy of the particles in the distribution beyond that point, which now have enough energy to cause a physical or chemical reaction to take place. And it's my belief, though I can't prove it, that what the hydrogen-occluded, hydrogen-host material does is it modifies the activation energy, and while the theory says something should happen, in the absence of it, the activation energy is simply too high and beyond our instrumentation. All right, so how would we then calculate the number of wall impacts to get our big number? As T increases, we see that the number of molecules and ions have higher energy. This is sufficient then to go ahead and impact it. So what we need to do, and we need to now reinterpret the energy distribution in terms of speed, not velocity, which is a vector, but speed, which is a scalar. And for those who've forgotten why the speed of light is designated by c, we need to do this in terms of celerity. Well, there again, we see the lovely equation at the bottom of the page, and we see 1/2 mc squared over 2, well, 1/2 mc squared. That's the energy of motion of the ions, and we see our 25 millielectron volt kBT in the denominator. All right, so what then does this curve look like? Well, it looks pretty much like the curve that we had for the energy distribution, but I was unable to find a nice pretty picture for things that went up to 300 degrees C, so I apologize, but you can see just looking at the curve that the tail of the distribution gets significantly larger the higher the temperature, and we see one of our nice happy numbers there, Locksmith's number, which is the number of molecules in a cubic centimeter, and we see the wall impact at STP, which is approximately 10 to the 22nd impacts per second. All right, so we can then calculate that, and it's remarkably simple calculation. The number of wall impacts depends upon only 2 parameters. It depends upon the number density of the gas, how many molecules are in the unit volume, and the speed of the gas molecule or ions that we're dealing with. And so for hydrogen, after you solve for the mean celerity down at the bottom of the page, which involves the molar mass of the gas, we find that it is approximately 1,700 meters per second, a pretty large number. Okay. All right. So here's the hypothesis that we're working on. We see 3 possible mechanisms that explain the behavior. The first one is, remember that at low voltage we have an equal number of positive and negative ions. Positive ions are neutralized at the high work function electrode and negative ions at the low work function electrode. To get them there, we have to diffuse against Frick's law. We have to do uphill diffusion. Alternatively, we can use some electronegative gas. Hydrogen is partially electronegative. Nitrogen is a pretty good one. Oxygen is electronegative, but we're not particularly interested in filling ourselves with oxygen and hydrogen at the same time. Or, as a number of people know, there are those in the room who have, or in the community, I should say, who have said that perhaps electrons are simply emitted by the hydrogen or deuterium occluded hydrogen host material. If that's the case, that makes the device work even better, because now we don't have to have the molecules go all the way to the electrode. They can capture the negative charge that's been emitted some short distance away from the electrode. All right, so let's make a simple approximation. Let's, again, just to make things simple, let's assume that an EV, electron volt, is required to remove an electron from the hydrogen host material of palladium. All right. If I have 1 million wall impacts per square centimeter per second, and I transfer but a single electron out of those million possible impacts, because a lot of them aren't going to be above the activation energy, so we have to be careful that we get the right activation energy, then we see that this is going to give us something of the order of almost 2 milliamps per square centimeter of current, compared to the few hundred microamps of current that we are currently achieving. So I believe that there is an opportunity to get significant increase in elect performance.
We've used other electrolytes.
Oh, yes. Well, okay. Now, it turns out that we have also conducted experiments. Since remember, all we need is we need positive ions and negative ions to interact with the electrodes. And my chemistry professor in college insisted that we know exactly what the pH of water meant. And what it means is that water is full of positive and negative ions. That is, your distilled water is full of ions.
And who was that chemistry professor?
Linus Pauling, yes. So anyway, so we tried that. Then we tried gel, and we find that, and one that we've used because it is reasonably inert, we found that ethylene glycol, again, spontaneously has a distribution of positive and negative mobile ions. And so while a gas is very nice because it tends to not have chemical reactions with the electrodes, there are other materials that can be used, and we're looking forward to solid materials being used because we discovered that high temperature epoxy. And other things that when I then discovered what was going on, I tested some materials. Ceramic tile, it works as an electrolyte. Even a glass microscope slide works as an electrolyte, which isn't too surprising because of all of the sodium ions that are present in ordinary glass. All right. So the LEC model hypothesis produces the conditions needed to transfer the measured LEC current densities. Frank, take over.
Oh, okay. So the conclusion and implications, the model analysis supports the experimentation that we've been doing. In fact, I was hoping to bring a demonstration of the lighting, LEC lighting being LEDs, but with this model being developed, we focused and did a lot of additional experiments, particular configurations and so on, and so that's what we've done. But the experimentation indicates that there are a lot of opportunities to improve the performance. As we said, the analysis we've used was for gas, but the same electrolytes that have the right properties will also do the same thing. Devices similar to electrolytic capacitors have been constructed and tested, and they produce a voltage, and I'll show you a couple of pictures of that. And the exciting thing about this is if we could figure out how this works, there are thousands of companies that make electrolytic capacitors, and this could be in production almost immediately. And I bought 10 of them for $10 through Amazon, so they're not expensive. I cut them apart, and here's 2 of them I cut apart. One of them, I unrolled it, and it has about 50 centimeters or about 20 inches of length in the when you unroll it. And in one of them, I had some copper screen that I had co-deposited palladium on, and I just cut it in strips about the same width as the the width of the electrode, stacked them lengthwise, rolled it up, wrapped it up. That's the one here on the left. Wrapped it up with the pipe tape, you know, as a way to hold it together, and then put a layer of silicone rubber on it. You smeared it on because the paper in the electrolytic capacitors, if it dries out, and so I wanted to keep the whatever the material was, the electrolyte there, I wanted to keep it in play. The second one here, I did the same thing. I cut it open, only this time I just spread some particulate on one of the electrodes. And both electrodes are aluminum, by the way. They just have a different treatment. And it produced a voltage and current. So I don't know, by the way, if there's some chemical reaction going on here or not. You know, I'll take them apart when I get back to San Diego and next week. But the fact that this might be a way to turn these into a product, I think, is very exciting. So, couple additional points. Last November, we took 2 cells to Texas Tech. Rob Duncan has the mass spectrometer system there that he's talked about in various committee or various meetings, and he offered to test our gas, so we took 2 cells there and had the gas tested. And a couple of interesting things, that they did not find any water, they didn't find any oxygen in the cell, and which surprised me a little bit because we didn't have a real high vacuum pump. But what I had done to fill the cells initially was I pull a vacuum, fill it with the hydrogen from the tank, pull a vacuum, fill it with the hydrogen, do that about 3 times. And I figured by that point I'm down to the purity level of the hydrogen in the tank, which, by the way, wasn't all that high. It was, I got it at a local welding supply, so it was not lab grade purity. But anyhow, that worked pretty good. They did find some helium-4, no helium-3, but helium-4 in the cells. But the one cell had been operating for about 7 years, and it had a nylon fitting at the top that helium would diffuse into, and so the partial pressure says it would helium-4 could diffuse in that way, and the other one was the glass cell, and again helium would diffuse through the glass, so we couldn't make any definitive statements about that. So we took the cells back to San Diego, and I took the glass cell, I refilled it with hydrogen. I took an identical glass jar, filled it with hydrogen, put both of them together in a metal box, and then I didn't have a way to pull a vacuum on the box. It was not strong enough. So I filled the box with pebbles, basically, small rock, and it left it operating for about 4 months, and transferred the gas to 2 lecture bottles that Texas Tech had sent, and sent that to them early in August, and they did the testing, and basically they found helium-4 in both of the tests, and it turns out the blank test, or the blank jar, had a little bit higher concentration of helium-4 than the other one. It could be they were both the same, and maybe helium-4 was inside the lattice material in the one that was the so-called active cell. And I've got 2 reports, and I'm going to give them to Alan, and he can, you can post them on Linter Forum, or hopefully post them somewhere. So if you're interested in looking to see what the helium-4 levels are. I did talk about lighting LEDs, and I've got some data here, and I've actually put together a video or a PowerPoint presentation that we can loop through, and Jacques has a TV out here, so I can connect up, and if you want to stop there, you can see it looping through the PowerPoint presentation. We started, and let me see, I've got a picture here. Here's the setup. Here are 5 LECs stacked together, you know, so stacked in series. The Arduino is a way that I could control the off-on ratio easily, and I was trying to optimize how much current it was taking to light the LED and still produce light, and so that's what the Arduino was. It was not providing any power to the cell. In fact, the wires coming from here, one goes to the negative, and one goes to the positive on the board. Here's a photograph, the same thing. I turned the lights off and the room lights off, and so you can see that the light is on, and this remained lit for more than 5 hours. It did decay. The light being emitted did decay over that time, which is not unusual because we think we were losing more hydrogen out of the hydrogen host material. I turned it off, and the next morning I got up and turned it on, and it came back, and this time it lighted as it had been originally. So the hydrogen host material had refilled with hydrogen overnight. So where are we now? We're just 2 guys kind of having fun, and we don't have a lot of equipment that we think might really be helpful, and nor the expertise that is collectively resident here in this room. But so we're open to collaboration, and I'm finding out more people are trying LECs, and let us know. We do have 3 patents that have been issued and 2 patents that are pending, but those patents kind of cover the basic systems that we've described, and if someone comes up with a better material or a better electrolyte or whatever, get it, you protect it, or whatever you want to do. Our patents aren't any good unless we can produce useful devices, and so if you can come up with something that helps make these useful, then let's get together and take advantage of that. And we've got our contact information here and our website, www.inoval.com. When we formed this company in 2017, and Inoval is a combination of the words innovation and novel, and that's kind of nice, but the thing that sealed the deal was Inoval.com was available. So, so anyhow, we've got that, and we do have a website that we put up there. So with that, I think we finished within our time, and we may have time for a few questions.
So let's start some questions. This was a double session, so we have double question time. We have 10 minutes, so let's use it very well.
You may want to.
Thank you, Frank, and Harper. Yeah, superb. I know there's something you briefly mentioned in your presentation. You have one of your very early LECs still functioning. Perhaps you could tell us something about how old it is.
How old is it?
I don't know.
It's probably at least 8 years. At least 8 years old, and I go to Harper's 2 days a week. Monday and Thursday. I prepare the cells at my house, take them to his house, and then he has the instrumentation and the kiln and things to heat them up and conduct the tests. So when I am there, we reverse the polarity of going into that cell, and you can see basically what we are observing is the flux going in and out of the palladium, which is why we can see even with the very low voltage that we have here with elect cells, it's enough that the palladium is going to be going out. So we do that twice a week and observe the flux, and the voltages go up. It goes up quite a bit, from maybe operating a fraction of a volt at the instrumentation, and it may go up to 80 or 100, 130 volts and then decay back down.
Thank you.
Lutz?
What is the highest voltage that your LEC can produce?
Determined by
Yeah,
the difference
yeah.
in work function of the materials.
Yeah,
And
this-
that typically is a few volts.
Yeah, we typically see with the materials we use, when we have open circuit, and we consider 10 megohms to be open circuit, we'll get somewhere around 900 millivolts, 9/10 of a volt. In fact, when we see more than that, we begin to wonder, is there some chemical reaction going on here? So though, because the difference in work functions, the difference in Fermi levels, that's about the limit based on the materials we're using. Now, if we use cesium or something like that may have a low work function, we may be able to get a little bit higher, but that's typically what we see. That's the reason I had 5 of them stacked here, and they produced enough voltage to light the LEDs.
Matthew?
Thanks. Hi, thank you for that. This might sound a really stupid question, but how is it different from a galvanic cell where you have 2 dissimilar metals electrically in contact with an electrolyte, which would just produce a voltage from chemistry? I know it might sound really stupid, but
You would think, how's the difference from galvanic cell?
Basically, what we do, I like gas because I don't want to have that chemical reaction take place. And so the problem that we have is the same problem that Volta had 200 years ago. That is, we're dealing with an electrophysical phenomenon. It's very easy to turn it into an electrochemical phenomenon. And he observed, because he was using water as his electrolyte, as soon as he switched to zinc, everything worked very good when he was originally using tin as his low work function material. And of course, we know that the hydroxyl ion reacts with the zinc, turns it into zinc hydroxide, and releases 2 electrons. So basically, be careful.
I guess my point is, how is this not So I'm thinking of Lena and like nuclear energy driving this, but if the metals are dissimilar, I mean, that's basically how a battery works, right? When you make a battery.
Yeah, well, that battery is working on electrochemical.
Yeah. So how?
We're not working on electrochemical. We're working on electrophysical.
But I guess how do you know that it?
Well,
Sorry. Okay, so great. So it lasts how many years? 8 years. 8 years. So then a question on the 8 years bit: can you measure how much energy you've used in that 8 years? Because if you had a very, very tiny current over 8 years, I mean, I'm sorry to kind of be a bit direct, but I'm just trying to understand. Because if the 2 metals were the same metal, then you wouldn't have any questions about this because there's
no, actually, if the metals are the same, it'll still work.
Okay, well then
It does.
in
It
which
works
case,
because remember in the differential equation we had D1 and D2 on the there, and the negative ions have a different mobility than the positive ions, and therefore you will get a current. Darrell pointed that out in 1932, and in fact, the people in Portugal who are building the cells to use relative humidity use 2 gold electrodes, so they are using 2 electrodes of the same work function, and yes, they get a very small amount of voltage, but it will work, and it's based entirely upon the diffusion rate of the 2 positive and negative ions.
great, thank you. If you've got the same metal, then my question is kind of null and void, so thank you.
Francesco?
Okay. First one, sorry because I arrived late. I have another meeting. So we have done this recent experiment. We have electrode and counter electrode distance 2 millimeters. We've done 3 experiments. Which one at the beginning under vacuum, and I heat up to 800 Celsius, and after stop, and measure the voltage anode and the counter electrode. The voltage is really few millivolts only. The second one, I had helium, and the same point, and the voltage of the order 100 millivolts. Later, the third one, I load the wire by hydrogen, and the voltage is close to 1 volt, but is decreasing when the temperature decreases. So I don't know if our data are in conflict or agree with your data.
Okay, well, here, the cell here is the one that's been operating for a long time. And it's got
The pressure with the gas is about 200 millibar.
Yeah, this has about 6 millimeter separation between the outer wall and the surface here. And this one still produces a voltage and current when we take away all of the external voltage. In fact, we took this cell with us to Texas Tech, hooked it up their voltmeter to make sure it had survived the trip all right, and it was doing fine. But so that was 6 millimeters. Now, as the model shows us, the math shows us, we think we can reduce recombination if we get the cells, the electrodes closer together. Dave?
Last question.
I forgot. The electrode is constantly loaded with low working fashion materials. It emits electrons. The counter electrode is just constant and iron.
Okay.
Clean.
Why don't we, let's talk afterward, okay?
Speed question.
Thanks very much. What do you consider the strongest evidence or argument for this being nuclear?
I don't know, we think that LE and R might be involved. And tell me what your definition of LE and R is. Because, we have a lot of experiments that do transmutation there. In other words, we may not need to get 750 keV to produce a, quote, nuclear event, but we may get, all we need to reduce the activation level energy may be available in virtually everything. In fact, our particulate, the stuff that John Paul used has worked. So that could be available. A low level of something like that could be all we need for this. Now, is that?
Yeah, so it sounds to me like the question of whether or not nuclear reactions are involved is still an open question.
Still an open question.
Yeah.
Definitely an open
Thank you.
question.
Yeah, by the way, in the very first slide where I show, we have to, or the slides where they have to be connected here, if in the Bark studies, that they did, they couldn't detect anything. And I don't know enough about the experiments to know, but they would have had to connect their test electrode with the lower work function or something if they wanted to change the Fermi levels, which then may give an opportunity to have some form of radiation. So maybe this explains why they did not find any radiation. But like I say, I don't know enough about the experiments. I read the paper, and who would have thought that they would need to write something like that? So.
All right, well, that's the end of the question and answers. Please thank our speakers.
I have one more.